All right, let's continue on our journey trying to make limits a bit more formal. There is another case that we haven't talked about yet, which has to do with asymptotes and infinity. So let's try to motivate this one. We're pretty good with holes so far, and we're getting better at jumps and with piecewise defined functions. But what happens if our function goes off the grid? So the intensity of light near a light bulb. If you take some physics or engineering, this is a really good one to think about. It varies something like this: y equals c over x minus 1 squared, where c is a constant of some kind. 1, I pick that number 1. What does that 1 mean for us? It means that if we're on this grid, our light bulb is at the number 1, and we are somewhere else looking at this light bulb. And what this should be telling you, if you look at it, is as x gets really close to 1, this denominator is going to get really small. And as that denominator gets really small, this overall fraction is going to get bigger and bigger. If I divide by a small number, I get bigger and bigger things, right? If I divide by 0.1, it's the same as multiplying by 10. If I divide by 0.01, it's the same as multiplying by 100. So this thing gets bigger as x gets close to 1, as it should. Because as I get closer to this light bulb, it should be brighter and brighter in my eyes until eventually it hurts my eyes. And then I close them. But still the intensity is up there. Now what actually is happening at x equals 1? This is really the model that we use. The c is a little bit more specific. It's some constant. But if you're trying to ask, is this a good model or what's happening, we should be evaluating what is happening at the extremes. What is happening at x equals 1? Luckily for you, are familiar with a lot of basic functions. And here's where it's going to be super helpful for you if you know what 1 over x squared looks like. In fact, let me make this a little smaller here. Okay, so 1 over x squared is one of those basic functions you should know. It kind of looks like 1 over x, like a hyperbola, except for that x squared makes it positive on both sides. So it looks kind of like this. Okay, it's a good one to know. If I multiply it by c, it's just going to get steeper. It's going to stretch it vertically. If I subtract by a 1, it's going to move it 1 to the right. So what's going to happen, if I draw over myself over here, is it should look a little bit like this. Oops, never quite getting there. And a little bit like this. Okay, I'm going to clean that up a little bit here. Okay, and you should recognize this phenomenon. This little line right here has a name, right? This thing, over here it's x equals 0. Over here it's x equals 1. Those are called asymptotes. Now I should say the asymptote is the line itself. So it's not like a concept in your brain. The asymptote here is x equals 1, and the asymptote here is x equals 0. It is that line. And if you wanted to say, oh yeah, there's an asymptote, what is it? It's x equals 1, or it's x equals 0. Okay, those define a vertical line. So those are vertical asymptotes. And this section is really about vertical asymptotes. Now, forgive that these are not to scale at all, but this vertical asymptote is telling you that as you approach this light bulb, that intensity is going off to infinity, and that your model is going to break down if I get too close to this light bulb. In this case, it will get brighter and brighter and brighter, but probably your model just doesn't quite work at 1 here. But there's lots of cases where it kind of does work and it's telling you something different, like the length of a shadow as the sun sets. Eventually that does go off to infinity, and that is telling you something meaningful, right? Which is that as the sun sets, at some point, that shadow doesn't have an end to it, right? It just goes on forever because the angle has gone to 0. So there's lots of cases where it's telling you there's something weird about your model, and there's lots of other cases where it's actually telling you something insightful about reality. So how do we relate this to limits? What an asymptote is doing at its heart is saying there is a behavior as x is approaching that asymptote. but we don't want to look at the number itself. In this case, we cannot plug in 1 up here. We cannot plug in 0 over here. And so that's telling you this is probably a really good case for a limit. So let's go ahead and write this down. The limit as x goes to a, as x approaches a, of f of x equals infinity. This may be the first time you've ever used infinity properly in your entire mathematical career. I hope you're excited. So we say this if f of x can be made arbitrarily large, as big as you want, by ensuring x is close to a. So this is how we're going to deal with this kind of infinity right now. So maybe focus on this 1 over x squared. It's a little nicer. I say, hey, that thing is going to infinity as x goes to 0. And you're like, I don't know if I believe you. Does it get to 10? Or rather, does it get to 100? And I go, yeah, it gets to 100 as long as x is within 0.1 of 0. And you go, okay, I don't know if I believe you. Does it get to 10,000? I say, yeah, it'll be at least 10,000 or bigger as long as you're within 0.01 of 0, right? Just getting a little closer and closer. Okay, does it get within 100 bajillion? And I don't know what the x has to be, but as long as I'm close enough to 0, it will stay above 100 bajillion, which is a made-up number. It's not really a thing. Don't tell anyone I told you to use the number 100 bajillion. Anyway, that's what it means to go to infinity. It's talking about behavior. And this is a little bit different than saying this limit exists. Properly, this limit doesn't really converge. It's really communicating something about the behavior. And so people use a lot of fancy language. They say it diverges to infinity instead of converges. They tie themselves up in knots about the language around this because this is sort of a loophole. That we would often say this limit doesn't exist, but by the way, hey, it diverges to infinity to tell you something more. I'm not going to worry too much about that distinction, but you should be aware that exists. So we're just going to say that this limit is going to infinity, and that this is the proper definition for our cases for infinity as well as for an asymptote. So let's go ahead and do another example here. So just to round this off a little bit, I could very easily talk about the limit as x goes to 2 of negative 1 over x minus 2 squared. Should look a little bit familiar. And so there's a couple of ways that I'm going to think about this, but let's go ahead and graph it first. Really handy. You can practice your familiar graphs. So at 1, 2, this is going to look like that same graph from before, but it's got a negative, so it's going to go down. Just like that. And as x gets closer and closer to 2, this denominator is going to get closer and closer to 0, but it's always going to stay positive because of that squared. So I get this really, really big positive number, and I get a minus here, and it goes down to 0. Okay, and this asymptote right here, asymptote is x equals 2. And lo and behold, this limit is going to equal, well, we would say infinity, but we're going to be a little bit more specific. We're going to say negative infinity for when it's going down all the way. And in fact, people will often rewrite this entire definition up here with a negative here by saying it's getting as small as I want. Okay, so if it's going down on both sides, we'll say it's negative infinity. If it's going up on both sides, up along an asymptote, it's going to be positive infinity. Okay, let's break this down just a little bit here. Because a lot of times to do this, we're going to need to actually look at the one-sided limits. And I think this is a nice time to stop and think about one-sided limits. So if I go to 2 from the right, this function, I find it pretty helpful to go ahead and think to myself, okay, what is happening to this denominator? This denominator, as I get closer and closer to 2 from the right, is going to 0. If I try to plug in a 2 here, I get a 0. And it's often handy for me to also think, is it going to be positive or negative 0? Okay, so if I stay a little bit bigger than 0, sorry, a little bit bigger than 2, then a number a little bit bigger than 2, that's what this plus sign means, minus 2 is going to be positive, and I'm going to square it anyway. So it's going to be put a little plus there just to mean it's a positive 0, meaning it's not actually 0, it's getting closer and closer to 0. Okay, so 1 over 0, a little tricky to think about at first, but as I divide by smaller and smaller positive numbers, this whole thing, is going to go to negative, because of this negative, and then infinity. So if I've got a constant up here divided by a positive 0, that thing's going to go to infinity. Because as I divide by smaller and smaller numbers, this whole thing is going to get bigger and bigger and bigger. Make sure that makes sense to you right now too. That if I divide 1 by smaller and smaller numbers, it gets bigger and bigger, and the sign depends on the sign of the top and the bottom here. This minus sign is carrying through to make it a minus. Always tricky the first time you do it. Let's go ahead and do this again actually on the other side, because I think it's worth it. So if I go to 2 from the left, then this thing on bottom is going to go to, well, if x is going to 2 from the left, that means it's a little bit smaller than 2. So if I have a number a little bit smaller than 2, and I subtract 2, I'm going to get a 0, but it's going to be a negative 0. Okay. Anything on the left means less than 2. And that sign's going to carry through. Rather than like a 0.1, we'll get like a negative 0.1, a negative 0.01. But the thing here is that whatever it is, we're going to square it. If I square a positive number or a negative number, it's going to be positive. Okay, so this is just going to be positive because that's squared. Everything on this denominator is going to have to be positive because it's squared. Okay, so this whole thing, and you'll see me doing these little arrows a lot, right? The top is going to 1, the bottom is going to 0 in a positive direction. 1 over positive 0 for us is basically infinity. That's going to be the behavior. But this minus sign out here is going to hang out, and I'm going to get another negative infinity. And that's what we see up here. From the right, I get negative infinity. From the left, I get negative infinity. And that's the right way to think about these asymptotes. I could talk about the left and the right, but in order for this limit to exist, again, the left and the right still have to agree. Okay, so let's make this asymptote business a bit more formal. A definition is always in order. Definition, a function f has a vertical asymptote at a, so at some spot in your domain, at some constant, if either of its one-sided limits is plus or minus infinity at a. So let's see what this means in practice. Hopefully, if you think of vertical asymptotes, you immediately think of 1 over x. It is usually our canonical example. In your mind, you should know what 1 over x looks like. Something kind of like this. The shape is called a hyperbola. That's a terrible drawing, but you too should feel empowered to make terrible drawings just to get across that you kind of know what's happening. If you can do quick sketches, it'll go a long way into helping you understand a situation or not make mistakes or communicate what's going on. So roughly speaking, that is what 1 over x looks like. It has a vertical asymptote at x equals 0. I'm saying this because I hope that you learned that in pre-calculus, but if not, here's your reminder. It goes off to positive infinity on the right and negative infinity on the left. Okay, so how would we, if we didn't know that right away or we wanted to show it more formally, which we do, how would we show that y equals 1 over x has a vertical asymptote? Well, we could just take a one-sided limit. We could say, hey, the limit as x goes to 0 from the right of 1 over x is equal, actually let's even go a little slower. Well, what's happening here? As x goes to 0 from the right, this x is going to 0. From the right means it's going to stay positive in this case. It's always going to stay a bit above 0 here. This is going to 1. If I have a constant on bottom, constant on top, a non-zero constant on top, and a 0 on bottom, you can darn well bet that whole thing is going to go to infinity. The only real question is positive or negative. So in this case, I have a positive number on top divided by a positive number on bottom. It's going to go to positive infinity. And that's it. That is enough to say that this has an asymptote at x equals 0. So this has an asymptote x equals 0. The second you know either of those one-sided limits goes off to plus or minus infinity, that's what it means to have an asymptote. We could, just for fun, we could go from the left-hand side, a little bit of practice here. In this case, the top is still going to 1. The bottom is now going to 0, right? X goes to 0. From the left, meaning it's always going to be a bit less than 0. And we can ask ourselves, what's the behavior here? Well, if the top is not 0 and the bottom is 0, it's going off to infinity, right? At least if this is approaching 0. As that denominator gets very small, the whole thing is going to get very, very big as you like. The only real question is positive or negative. So in this case, the top is positive, the bottom is negative. A positive divided by a negative is a negative. And if you're unsure about that, go ahead and just plug in some numbers. Play that table game for a second and see what's happening here. It should match our fun graph here, right? From the left, if x stays less than 0, this thing is going off to negative infinity. It's going way, way down. And that's what we mean by negative infinity, is just way, way down. Positive infinity means way, way up. It actually means a little bit more than that. It means up without end, right? And down without end. And it stays there. Okay. What this tells us is that if we're going, if we get infinity from the right and negative infinity from the left, then this tells us something else. Give myself a little bit more room here. Whoop. It tells us that the limit itself, no direction, just going to 0. Worth thinking if you know what the answer is here. But in this case, the limit from the right does not agree with the limit from the left. I know that they're both infinite, they seem like the same thing, but you don't get too much further apart than positive infinity and negative infinity, right? So that is quite the jump. That is an infinite jump happening there. We're just going to call that an asymptote. And so we're going to say this does not exist. Okay, so the only way we're going to say this limit would exist is if those two infinities agreed, and then we could say it was positive infinity or negative infinity. Okay, and that's really what we're looking to check on these asymptotes, is really what is the left-hand behavior and the right-hand behavior. If you have an asymptote, or you think you do, or really you're just dividing by 0, you sort of have to come in from the two sides separately to see what's going on, until you get a lot of experience that lets you sort of see through to the end of problems a little bit faster. Okay, so let's do another example. I'm going to do this one a little bit quicker here. 3x over x minus 5. You could try to graph this in a calculator or on your computer, but I'm going to just break this up into parts real quick here. The limit as x goes to 5, that's when that denominator is 0. That's where I suspect I might have an asymptote of 3x over x minus 5. And let's go ahead and take this one from the right. Well, the top is going to 15. Nothing wrong with that. The bottom is going to 0. This x is staying bigger than 5. So a number bigger than 5 minus 5 is going to be positive. And we're going a little fast this time. Non-zero over 0 is going to be infinite. Positive over positive is going to be plus infinity. Okay, and similarly, I'm going to do the left side also at double time. You should just see if you can do them at all, and then check with my answer here afterwards. If I go from the left, this is still going to 15. You definitely don't need to worry about positive or negative 15, because 15 is always positive. A little bit smaller than 15 is still positive. However, on the bottom, as we go to 0, 0 is that magic dividing line in between positive and negative. So if we put a 0 here, if I stay less than 5, then little less than 5 minus 5 is going to be negative, which means this whole thing is going to a positive over a negative is going to be a negative infinity. And again, what this means for us overall is that the limit without those one-sidedness, the two-sided limit, is what we call it, of 3x over x minus 5 does not exist. So it has a left-handed limit and a right-handed limit, or rather it has an infinite left and right-handed limit. So it has an asymptote. You only really need one to show it has an asymptote of x equals 5. But the two-handed limit, we're going to say it doesn't exist because the left and the right infinities don't exist. Okay, one more. This is one I really need you to know. This amazing function, y equals natural log of x. It's a great example of a function with an asymptote. And you should right now check, do I know what this looks like? Boy, is it helpful if you know what natural log of x looks like real quickly in a sketch. So this is me doing a real quick sketch. And I don't need much more of you other than to say, oh yeah, natural log of x looks kind of like this. Okay, it has this vertical asymptote. Here, we'll do this properly here. It has a vertical asymptote here of x equals 0. And then it goes off to infinity off to the right here. It crosses, if I were to have drawn this to scale, it should cross right at 1. So the natural log of 1 is 0. Natural log of 0 is, say it to yourself, doesn't exist. Natural log is not defined for 0 or negative numbers. So natural log is only defined for positive numbers. It goes off to negative infinity as we get very, very small. It goes off to positive infinity very, very, very slowly as I go off to the right. It grows very slowly. Okay, and then at 1, it is a 0. It is also the inverse of e to the x. So I'm going to try to do this real quick here. If I were to graph e to the x, to scale as best I can, what this should look like is the reflection of e to the x over that diagonal y equals x. If I take an inverse, I'm just switching all the x's and the y's. So e to the x is always positive in its range, which means the domain of natural log of x has to be always positive. The domain of e to the x is all real numbers, so the range of natural log of x has to be all real numbers. They just switch their x and their y values. A little reminder on inverses. Okay, so point being, natural log of x has an asymptote. And let's go ahead and write this out. That the limit as x goes to 0, I have to say from the right. I have to because natural log of x is not defined for negative numbers. So this limit wouldn't make much sense as a two-handed limit. It really only makes sense as a right-handed limit. So the limit from the right of natural log of x, we're going to do this just by looking at the graph. You could make a table of numbers if you want to, or you could even argue it because you know what e to the x looks like. But looking at this graph, as I get really close to 0 from the right, this thing is going down to negative infinity. This one sneaks up on people. All kinds of things with natural log sneak up on people. But this is a great example of a vertical asymptote that only exists for a one-sided limit because the other side, the function isn't even defined. X equals 0. All right. This, people, if you do more math or physics or engineering or really any kind of stats or modeling, understanding that natural log has a vertical asymptote at 0 is something people are just going to assume that you know and can communicate about. It says a lot about the kinds of transformations you can do with e to the x in natural log. Super duper important. Okay, so that was some great examples. I intentionally tried to pick ones that looked different from each other, and hopefully you'll start to feel better as you work through some homework problems.